Hi, everyone. Welcome to the last keynote of the AI Day at SINFO. I hope everyone is having a great time. So I'm going to introduce our next speaker. Most of the AI we see today is built for a small fraction of world's languages, but our next speaker is changing that. As a member of technical staff at Cohere, she is a specialist on how large language models actually learn from data. She led the pre-training and tokenization for the Tiny Aya project, a groundbreaking model that packs the power of 70 different languages into just 3 billion parameters. Her work is about more than just efficiency. It's about making sure the future of technology belongs to everyone, regardless of what language they speak. Please welcome Diana Abagyan.
Thank you for your patience. I'm sorry about that, but I'm presenting on the Tiny Aya family of models today. So yeah, we talked about do people typically tend to use AI in English or in another language? And generally, if people speak English, they use AI in English because the quality is just not comparable, unfortunately. But we're trying to improve that. So this is what Tiny Aya seeks to solve. Tiny Aya is a family of really small models, 3.35 billion parameters, which I don't know if you're familiar with like the scale of model size these days, but that's pretty small, unfortunately. So it can run on your phone. And that's very different from, for example, like ChatGPT. That's an absolutely massive model. And we do geographic language coverage over 70 languages, so very broad language support as well, and that was our priority. So this release includes a base pre-trained model, Tiny Aya Global, which covers all of the languages shown in the diagram, all 70 plus, and also 3 cluster optimized models. So in this talk, I'm going to be going into some of the design decisions and sort of just research decisions that we had to make when creating a model that is intentionally designed for multilingual support and not as an afterthought, and how to make it efficient, but also competitive on all of these languages. So first I'm going to be talking about tokenization, then pre-training and post-training. And I want to be very clear, this is a small selection of problems that we had to face in this project. So if you want to see more, you should check out the tech report on this slide. Okay, so first I'm going to go into tokenization. Language equality starts at the tokenizer, which is the very first step of any language model. And so the question here is, how can we design an equitable tokenizer with broad language coverage? If anyone here is unfamiliar with tokenization, I'm going to do a brief explanation. So computational systems generally require input to be discretized, which means breaking it up into chunks for processing. So for language data, this process of breaking up text into parts, which are called tokens, and converting them into a numerical representation, that's called encoding. This is all called tokenization. Nowadays, we use subword tokens, which allow for a smaller vocabulary. So instead of your vocabulary being all of the words in the English language, which is like over 1 million by some estimates, you can have just something like a syllable. So maybe like 100,000 vocabulary, which this is kind of towards efficiency. We want our model to be as small and as performant as possible. So yeah, nowadays, everyone uses subword tokens, and tokens in general are learned by identifying frequent subword patterns in the training data that result in the most efficient representation. So at the bottom of the screen, at the bottom of the slide, I have the same text tokenized in different ways. There's a lot of different ways you can go about it. Now, multilingual tokenization is often inequitable. Sometimes what's done is just an English tokenizer is reused. Other times, the other languages besides English are extremely underrepresented in the training data, so you don't have efficient representation of non-English languages, but especially non-Latin scripts. So yeah, this kind of follows a pattern of, in NLP, other languages can be treated as an afterthought, right? Now, why do we care about efficient representations in tokenization? If you don't have an efficient representation, sequence length is really long. This can give you a worse learning signal during training, so you would have a worse performance on that language. After training, the inference would be slower, so it takes longer to generate something from the model. Another thing is higher API costs for non-English speakers. So this image on the right shows an example of the same sentence, what is the capital of Morocco, written in English and written in Greek. And the colors underneath represent tokens. So you can see the English one has very few tokens, maybe like 7, if I'm counting correctly. But the Greek one is not being tokenized correctly, and so there's a lot of different tokens. So this is more expensive, and the performance is not going to be as good. And if I remember correctly, this is ChatGPT. So people are trying to use these very popular models in their native languages, and it's just not designed to support them. So our innovation was to directly intervene in the tokenizer training. We weigh the data of different languages according to this formula that I have here. But essentially, you don't have to understand the formula. Basically, we balance the natural data distribution, so the availability of data in every language, with groupings by language script and language family. These buckets are more likely to share tokens in between them. So we want to make sure that every grouping of languages is properly represented, but then we have to balance it with the availability of data. So yeah, together that comes into this innovative formula. If you want more information, you can check out my paper underneath. And yeah, so in the end, that's what we use for our tokenizer for all of the models. So the tokenizer is shared. And because there's so many languages, we use a fairly large vocabulary size, 262,000 tokens vocabulary size, which is on par with some other models this scale. And we trained on 50 gigabytes of data. And in this image, you can see the tokenization efficiency by script. And as a reminder, the less tokens, the better. You want as much compression as possible. And our model, TinyAya, is represented in green. So comparing to the other models at this scale, Quen, Gemma, and small LM, we beat the efficiency, tokenization efficiency in pretty much every script. Either we beat it or like we're on the high end. So that's a very good sign as we're going into training. Okay, next topic is pre-training. So how can we train a competitive base model across all languages when multilingual data is scarce? This is a question that plagues multilingual NLP. And I want to give some background on the issue first. So this is what I'm calling the pre-training data language gap. Has been studied a lot. This paper linked underneath is a really great intro if you're not familiar with the idea. But essentially, the data available on the internet is overwhelmingly in English. I'm sure all of you are aware, just in your experience on the internet, right? And then there's a handful of high-resourced languages that trail afterwards. So after English, the most highly resourced are Chinese, Spanish, Arabic, French, and German. But the comparison of the data available is just like vastly, vastly different. It's so much bigger for English. This diagram that I'm showing here is Wikipedia data. So Wikipedia is actually better balanced in terms of multilingual support, but still English is by far the most available, as you can see from the size of the dot. So yeah, this means that the majority of models are optimized for English in particular, and then multilingual data, it's kind of just like whatever is available. Why is this important? This means speakers of languages other than English will have unequal access to technology. So this exacerbates existing social, linguistic, and cultural inequalities. And we want to make sure that there's good technology available for everyone around the world. Another thing is model safety. I'm sure you've seen examples of cases where generative AI responds in a very unsafe manner or even incorrect manner. And this is worse with lower data availability, and it's worse with lower resource languages. So for more information, you can check out this paper. But that's why in the pre-training stage, this question is really important to us. How did we approach it? We crawled across more data. We built a large corpus we used Common Crawl, which is a large corpus of public data from the internet, in some proprietary text as well, to create a data set of all of our training languages, over 70 languages. In the training mix, we upweight languages other than English and low resource languages in a similar manner to how I described in the tokenizer training. And quality filtering is also extremely important, as we were talking about with the safety issues. So first we do language ID, and there's a stop word list. Then we use some heuristics from raw data to filter as well. And we also deduplicate the data. And we classify according to domain and difficulty. So you want to use those classifications to upweight more informative domains, such as educational domains, and downweight lower quality data to try to help with the safety issue and just improve the model quality overall. Okay, now we're going to go to post-training. So how can we create high quality data that pushes the boundaries of what our models can do across many different languages? If anyone's unfamiliar, in the post-training stage now, instruction tuning is very popular. A lot of different methods are popular where basically you take really high quality data sets and train the model further for a smaller amount of time and steps on that data. So this is where the capabilities of the model really come out. This is where it becomes usable. And for these like generative models, the instruction tuning is where you're actually able to talk with it more naturally like a chatbot. So the problem here is for lower resource languages, there's very little high quality instruction data available. If there's any available at all, that's also a problem. So we need to create more data, synthetic data that is high quality. How do people go about this now for languages other than English? The data samples are translated with machine translation. So again, I'm sure you all have your experiences with machine translation. It is not always perfect. There is a concept called translationese, which is like it's specific qualities of translated text that are unnatural to the way that a native speaker would speak that language. So you want to avoid training on that kind of artifact. Another way that you can go about it is learning from a teacher model. So taking a bigger model and creating data from it. Teacher models, however, we were talking about the lack of support for languages other than English. So if you're looking to learn from a teacher model, you don't have a lot of choice. And those teacher models, if they support those languages, then the quality is not as good. So we had to innovate some methods for post-training. And what we did is a multi-stage synthetic data pipeline, which includes reducing translation artifacts, this translationese, and using multiple teachers. Large diagram, you don't need to understand all of it, but yeah, in short, we start with these source data sets, and then we do translate them to all of our different languages. Then we assess the quality using Comet, and decide at that point, is the data set quality sufficient? For higher resource languages, it's likely to be sufficient at this stage. So for that sample, we would just translate it entirely and add that to our final data set. Now, in cases where it's not sufficient, then we use these methods that we developed. So one way that we go about it is translating the prompt only and doing this with a bunch of different teachers. And then you can combine all of these different generations into one. So I'll go into that in more detail. We also apply cultural transformations. So if you translate English data directly into other languages, you're going to be missing a lot of cultural context. Or it's going to be asking about things that are irrelevant. Like, I don't know how much you guys care about Thanksgiving in Portugal, but you know, we would be missing some Portuguese holidays if we were just translating directly from English. So we do these cultural transformations as well. But I'll go into more detail on it in the next slides. So yeah, first on the prompt level transformations, there's a few different types of transformations that we apply. One is naturalness. So you try to remove the translationese or the translation artifacts. Another one is cultural adaptation. And in this example image down here, unfortunately it's in German. I don't speak German, but I'll tell you what's relevant here. Basically, the original question is asking about Thanksgiving. The first direct translation in red it uses the word Thanksgiving directly from English, so it's not very relevant for Germans. In naturalization, the word Thanksgiving is converted to the German equivalent, which I don't know how to pronounce, but it's in bold, so again, now the data is more relevant to Germans. For cultural adaptation, this transforms the data a bit more than the other steps we've talked about. So Thanksgiving, even though it has a word in German, it's not as important for Germans as Christmas. So now the word Thanksgiving is changed to Christmas. Another type of transformation is difficulty. So this is entirely changing the sample actually, but it's making it more difficult. In this case, it's asking like, what's a grocery list that you would need for the dishes you're going to cook at Thanksgiving? If anyone speaks German, I'm sorry for my bad translations, but that's the gist here. And you wouldn't necessarily apply all of them. You pick and choose which ones you apply. But yeah, it can be really helpful for downstream evaluations because it makes the data more difficult and perhaps like it helps on downstream evals. So yeah, for more information, please check out this paper. Now, for fusion, the idea is to use the synthetic teachers that I was talking about. So you generate additional data with a few different models, which are called your teachers. And a very common strategy up until this point is to generate the different possibilities and then select the best of them. So that's called best of n. But in that case, you lose all of the compute that you used to generate the other completions because you're just not using it for anything, right? So in this method, fusion or fusion of n, you sample generations from different teachers, but then you combine them, you fuse them, and that data ends up having higher quality than if you just use the best of n one. So yeah, hopefully that diagram is a good enough explanation of what I just went over. And all of these different methods are combined into a model that is competitive in high resource languages, but also with comparable low resource language support. So in this diagram, you can see the green line is the number of pages in Common Crawl. So basically, it's a way to measure how resourced the language is, how much data is available in that language. And we have grouped bars based on how much data is available in those languages. So in the first one are the highest resource, like English, Russian, German, etc. And then at the end, we have all of the lowest resourced. This includes a lot of African languages like Yoruba, Hausa, etc. So again, our model is in green. And you can see that the green bars are competitive with the other models at every cluster of languages. But at the very end, where it gets lower and lower resourced, our model is way surpassing any other model at this scale. So this was our goal going into the model, is to have equitable language support. And there's not as much variation in the height of our bars, so the performance of this model across different languages. There's not as much variation as there are in more popular models like Gemma, which is from Google. So yeah. That was a lot of information, but I would be happy to take any questions at this point. Okay. I think there's going to be a microphone.
Okay, any questions?
Thank you for your speech. I'd like to ask why you think other big companies haven't also implemented this type of models, given the necessity. Would you think it's more for profit reasons? They don't see as much profit in lower, like these communities?
Yeah, that's a great question. I do think profit plays a huge role. So first of all, I think it started with just the availability of data and resources in English. In NLP, it was so much easier to start with English for a lot of these methods. But it's been decades since we started out. And these big companies, in terms of which languages they choose to work on after English or focus on after English, they tend to be the highest resourced, but the highest resourced also correlates with where their biggest markets are. So for example, like Chinese is a very highly resourced language, but is not big market for the Western world. So that's actually a counterexample of where there's like less support in Chinese from some of the enterprise models. Open source, so these models are fully released to everyone. That's called open source. Open source, there's a lot more focus on just like resourcedness in general. So Chinese is still a very competitive language for open source models. But then models from industry, since they're not looking to sell in Chinese markets, the support for Chinese is way lower. So yeah, I mean, this work is from our nonprofit arm. It's a research lab, so we're less concerned with profit incentives and really are just trying to make a model that works for as many people around the world as possible.
Any more questions?
Good afternoon. So thank you for your presentation. In Portuguese and in a lot of languages, you have a lot of variants. In Portuguese, for example, you have the European variant, the Brazilian one. I would like to know if you took that into account in your training, in your variance of data, and what's your approach dealing with that variance in the model, because that can input some noise and etc.
Yeah, that's such a great question, because on the one hand, it can introduce noise, but on the other, our goal is to support as many people as possible, right? So people who speak dialects or use like, you know, some sort of non-standard variations, we would want to support them as well. Dialect NLP is a very difficult question, unfortunately. And it's also about data availability. So you might have, for example, we used a lot of data from the internet, right? So in that mix, you have people using slang, you have people using different dialects, right? Whatever. It may be at a very small level that is not enough to, so for example, if someone prompts the model using the dialect, the output would not be entirely in that dialect, but there might be like a word here or there. So it's like not the way someone would naturally speak that language, right? It's definitely a huge problem. We were undertaking a big task with the 70 languages, so it's like, it's kind of hard for us to do dialects as well. Arabic dialect NLP is the most, pretty much one of the most highly researched areas of dialect NLP. So we included some Arabic dialects. There's also in Norway, there's like two different variants in how they write, I believe. So we included those as well to try to support both. But in general, with like small dialects, with not as many speakers, it's very difficult. But we're hoping that people will take these models and adapt them further to, you know, their communities. So continue the post-training and hopefully see better performance in those dialects as well.
Thank you so much.
How did you guys handle language isolates? So languages that are not part of any group family. So you had that
language
formula.
isolates.
Exactly. You had like that formula. You said that you guys like cluster languages that are in the same family. What about those?
Yeah. So we talked about this like language bucketing scheme during the tokenization and the pre-training, right? So especially for tokenization, the relatedness of different languages was very important. However, the single most important thing in tokenization is the script. Because you're using the surface forms of these words. So if the alphabets have nothing in common, you can't really share tokens. So for example, we had a few different African languages in our training. A lot of them are written with Latin. Pretty much all of the ones we used except Amharic are written with Latin script. So you actually get to exploit some benefit from, even though like to a human, they don't look similar at all, right, those languages? But the type of training that we're doing, it's called byte pair encoding. The text is converted into bytes. So that's what the model sees, is not even just the letters, but it sees the bytes. So you get to share a little bit there. So yeah, first and foremost, the buckets were formed by script. And there are languages where that is the only language that uses that script. And yeah, unfortunately, in that case, we still want to have good performance on them while not sacrificing performance on other languages. So we had this kind of complex weighting scheme where you would upweight the isolates in this case. But yeah, so even with shared scripts, since the language family is different, the letters are arranged in very different ways, even though they're the same letters. So we upweight those as well in our training and the tokenizer training.
Thank you.
You were saying that for languages that have smaller representation, you sometimes do a cultural adaptation. So with that example, you had Thanksgiving and then translated into Christmas. And then you also had the example of translating into a grocery list message. Mm-hmm. Does that mean that those languages will have less diversity in the type of data that they have?
Yeah, this I think is an excellent question. And it's definitely something you have to worry about with synthetic data. Since first of all, you're creating this data from another model. There's concerns that like whatever issues that model has will be propagated, right? But then with the difficulty transformation, there is a set list of tasks, or like, tasks that the model is more biased towards choosing. So you may be seeing let's say a narrowing in the scope of the different tasks that we have. Still, somehow synthetic data wins out. And I believe it's really important that it's not dominating the entire data mix. It is definitely high quality data that is important to have, but you still keep the broad general pre-training data in there at small percentages. They get smaller as you go out throughout the training, but they're still there. So the model doesn't forget the diversity of the data, even though it's noisy and messy, and in some cases maybe unsafe, it's still there. So hopefully the goal is to have the model gain all of those capabilities.
Thank you.
Hi, thanks for the presentation. My question was more of a curiosity. I'm not sure if it was included in those 70 languages, but do you think that these kinds of techniques could be applied to like languages with very few resources, like Esperanto, for example, which is basically
I don't believe we included Esperanto. But another thing I didn't focus on in this talk is that part of the design for this model is intended to make it easier to adapt to other languages after training is done. So this is in the tokenizer design as well. If you check out the paper that's linked on that slide, basically the finding is as many languages as you can include in the tokenizer, it makes it easier to adapt to unseen languages after training as well. And how would you adapt? There's a lot of different ways you can adapt, but additional training generally, right? So we have had some people in the greater open science community of Cohere Labs. There's an event called Expedition Aya where teams group up and they choose some sort of project to expand the tiny Aya work. And some people suggested, some people took on other languages that aren't included in tiny Aya. No one chose Esperanto, but yeah, it's something that you can easily do. If you already have a high quality model, even if the language you're trying to expand coverage to doesn't have a lot of data, it's so much easier to make that switch or like to broaden the coverage more because it's already high quality and has this characteristic we call plasticity, which means that it's open to changing which languages it supports.
Thank you.
Hello, thank you very much for the talk. I don't know if it's an alternative or something that can be implemented in parallel to what you guys did, but I didn't read the full tech report, so it might be included. But for example, for post-training, something that you also can do is reinforcement learning with human feedback, especially for neutralization as well. Mm-hmm. And my question is, was that something that was considered, or if you guys didn't, or decide against it, why?
Yeah, that's a great question. Unfortunately, it comes down to data availability. There is not a lot of data with human feedback available for multilingual languages. So the lab is actually trying to work on this, creating more data so that we can do that. But there was a little bit of RL in there.
Thank you.
Hi. So you've mentioned a little bit about sort of the amenability of the tokenizer of the model to be extended to new languages. Do you think it would also be amenable to tokenizer extension, where, for example, you have a new language with a completely unseen script? You don't want to just treat it like bytes with the existing tokenizer. You want to actually add more merges to the BPE. Do you think that Aya and its tokenizer have any particular advantage here?
Excellent question. If I'm allowed to go back. Here, this paper, we actually investigate this tokenizer design specifically for adaptation after training, so excellent question. Now, for extension is a really difficult question because, yeah, well, it also, like, if you're increasing the vocabulary size, you also have to add more embeddings. You have to increase the number of parameters in the model. So we didn't directly compare against that because it's much more intensive. There's also a lot of different methods to go about it. But another approach that you can do is just replacing vocabulary. So you keep the same vocabulary size, but whatever language or languages you want to support, you keep the embeddings that are shared by the new, like the languages you already support and the ones you want to support. And then the unused tokens, you basically use new vocabulary from the new languages. And then when you train further, you don't have to change the model size, you don't have to change anything, but those new weights are going to be randomly initialized, and you train further just to help those weights along, basically, instead of having to retrain the whole embedding matrix. So we compared that approach versus just using this tokenizer design where you use as many languages as possible in the tokenizer, essentially, and then the comparison would be just training further on the new language or languages rather than messing around and doing tokenizer surgery. So we found that this approach is actually more performant than changing around the weights and doing tokenizer surgery. So I would recommend checking out this paper, but it's definitely a surprising result for me, but I think it has to do with the fact that you're already using all the strengths and skills that the model has gained in training and just, you know, going a little bit further rather than having to reinitialize. But again, there's so many different methods in that area, and we did not compare against the most sophisticated. So there's probably more sophisticated methods out there. I think the advantage of this one is just how simple it is. Pretty much anyone can pick it up and train further. You don't have to like mess around with the internals.
Thank you.
Yeah.
Okay, thank you, everyone. If you want to ask further questions, Diana will be next up in our Connect stage. So can I ask for a round of applause for Diana's keynote, please?